Circular motion, uniform. Circular motion. This describes an object moving in a circular path with a constant speed. It's crucial to understand that while the speed is constant, the velocity is not, because velocity includes direction. The direction of the velocity vector is constantly changing as the object moves around the circle. This change in velocity means the object is accelerating, even though its speed isn't changing. Centripetal acceleration, _c. This acceleration is directed towards the center of the circle and is what keeps the object moving in a circular path. The magnitude of centripetal acceleration is given by _c equals sign v2r, where v is the speed and r is the radius of the circle. It's essential to understand that this acceleration is caused by a net force acting towards the center. Centripetal force, F_c. This is the net force required to keep an object moving in a circle. It's not a new type of force. It's simply the name we give to the net force when it's responsible for circular motion. The magnitude of the centripetal force is given by F_c equals sign ma_c equals sign mv2r. The centripetal force can be provided by various forces such as tension in a string, friction between tires and the road, or gravity. Examples of circular motion. Think of a car going around a curve. The centripetal force is provided by the friction between the tires and the road. If the friction is insufficient, the car will skid. Another example is a ball on a string being swung in a circle. The tension in the string provides the centripetal force. Gravitation, Newton's law of universal gravitation. This law describes the attractive force between any two objects with mass. The force is directly proportional to the product of the masses, m1 and m2, and inversely proportional to the square of the distance, r, between their centers, F_g equals sign g, m1, m2, r2, where g is the universal gravitational constant. Gravitational field. A gravitational field surrounds any object with mass. It's a vector field, meaning it has both magnitude and direction at every point in space. The gravitational field strength, g, at a point is defined as the force per unit mass experienced by a test mass placed at that point. Near the surface of a planet, the gravitational field strength is approximately equal to the acceleration due to gravity, g 9.8 ms2 on Earth. Orbital motion. Objects in orbit, like planets around stars or satellites around Earth, are constantly falling towards the object they're orbiting, but their tangential velocity is just right, so that they keep missing the planet and instead follow a curved path. For a circular orbit, the gravitational force provides the centripetal force, g r2 equals sign mv2r, where m is the mass of the central object, m is the mass of the orbiting object, and r is the orbital radius. This equation can be used to derive Kepler's third law, which relates the period of an orbit to its radius. Kepler's laws. While not always explicitly covered in as much depth in AP Physics 1, Kepler's laws are related to gravitational motion. They describe the elliptical paths of planets, the varying speeds of planets in their orbits, and the relationship between the period and radius of planetary orbits. Connecting circular motion and gravitation. The key connection is that gravity provides the centripetal force for orbital motion. Understanding this connection is crucial for solving problems involving satellites, planets, and other celestial objects.